This tutorial will illustrate how to set up a model for a modal time history analysis. Using either eigen or Ritz vectors to perform a linear time history analysis can be significantly more computationally efficient than using direct integration. Before we begin, note that the first or fundamental mode for our model has a period of approximately 0.2 seconds. This information will be used later in the tutorial. We will begin by creating a model using the 2D frame template with the default settings. We will go to the Analyze menu and set the analysis options so that we restrict the behavior to a planar frame. Next, we will verify that the mass source is from the elements. Now we will define the time history function to be used. We have many options to choose from, including using a record from a file. But for this particular model, we will use a sine function, which we will name TH_sine. Note that the default curve has a maximum value of 1g, which we will change to 2g, with a period of 1 second. We will leave the number of steps per cycle at 20, which gives us a sampling rate of 0.05 seconds. We will use a total of 5 cycles for our loading, and 5 cycles at a period of 1 second gives a duration of 5 seconds. We can move the cursor over the graph to obtain the coordinates at any point. Next, we define the load cases. We will modify the previously defined modal case to use Ritz vectors, which typically capture more response when compared with the same number of eigenvectors. Since we are only interested in the x-direction behavior, we will set the maximum number of modes to 2. With Ritz vectors, it is important to specify an applied load that is appropriate as the starting load vector. In this case, acceleration in the global x direction is suitable for our time history load case. Next, we will add a new load case for the time history. Switch to time history for the load case type, and we will do a linear modal analysis with a transient function. The load will be applied as an acceleration in the U1 direction, using the previously defined TH_sine function, with a scale factor of 386.4 to convert from G units to inch units. As stated at the start, we know that the fundamental period is approximately 0.2 seconds. For this example, we will use an output time step 1/10 that, or 0.02 seconds. With modal time histories, a finer time step here does not significantly affect the accuracy of the analysis. It simply provides more detail in the output. We will set the total analysis time at 10 seconds, which is twice as long as our 5-second forcing function, so we will need a total of 500 output steps. Now we are ready to run the analysis, which we will do with both the modal and time history cases. We will set the dead load case to do not run as it is not needed. With the analysis complete, we have numerous ways to display the results. We can display the member forces, on an individual time step basis, in this case 1.4 seconds, and then easily toggled to any other time step. We can also display the envelopes for the member forces. We have the same type of options for viewing the deformed shapes. And again, can view the results for any time step. As with any other analysis, we may also view the results in a tabular format. In this example, we will select joint displacements, and modal participation ratios for just the time history load case. The displacement table displays the maximum and minimum values for each joint. For the modal participation ratios, note that the values for the Ritz vectors are 100% in the x direction, as we hoped. One of the most enlightening tools available when doing time history analyses is the ability to create a video of the structure's deformation. With the deformed shape shown in the active window, click on the Create Video command. We will name the video Movie 1. We want the analysis results for the time history case, and we will limit the movie to 5 seconds, the duration of our forcing function, with a magnification factor of 5. The program allows us to save the video using different levels of compression. First, we will use the full frames option, which is uncompressed. This will create the largest file. The saved movie file looks like this, with a size of just over 54 megabytes. Next, we will repeat the movie creation process. This time saving it as Movie 2. All other settings remain the same. However, this time we will save it using the Microsoft Video 1 compression with a compression quality set to 75. Although the movie looks similar, the size is considerably smaller, just over 2 megabytes. Next, we will plot a response spectrum curve for a specific location on the model. We start by selecting the point on the undeformed shape where we want to generate output. In this case, the top right-hand corner. Under the Display menu, we select the Show Response Spectrum Curves option. On the various tabs of the form, we can change the joint selected or the time history case if there is more than one. Control what is to be plotted. In this case, we select period versus pseudo-spectral acceleration. Set the direction. And the damping values for the curves up to a maximum of 6. Here we will delete a few. We also have control over options, such as whether the spectrum should be widened or if there should be a grid overlay. The display shows the curves for the 4 damping values selected. Note that the peak value occurs at approximately 1 second, which matches the forcing function. Next, we will display time history traces for the same selected joint. Start by going to the Display Show Plot Functions command. Here, we can display any number of different functions. In this example, we will plot the X direction displacements for joint 9. The displacements will be plotted on the vertical axis, and we will plot them against time on the horizontal axis, although you have other choices here as well. We will save these settings as name set time history. This graph shows the X displacement versus time for joint 9. Moving the cursor over the graph gives time and displacement values. Note how the response damps out rapidly once the forcing function ends after the 5th cycle. Now we will display the deformed shape for the time history case once again, and then go back to the Create Video command. This will be movie 3. This time, check the Show Graph option with the time history name set. And then set the end time to 10 and click OK. The deformed shape movie is tracked against the plot of the displacement for joint 9. This concludes this tutorial on modal time history analysis.